Hey everyone, welcome to Professor Long's Lectures in Anatomy and Physiology. I'm Professor Bob Long. If you're watching these videos, then you are either enrolled in my course or you stumbled across them on the inner Google and you're watching them because you're looking for help in your anatomy and physiology class. Just know that these videos are designed for the students who are enrolled in my A&P courses, and these lectures are designed for the way that I want my students to learn the material at this stage of the game. I don't always go into the technical definitions of everything because early on, especially with a lot of students that may not have a lot of strong science background, you can memorize technical definitions and not know what they're saying. I did that early on in my career as a student. I could memorize lots of definitions and really not understand them, and I could still make an A on a test. My goal is for my students to understand the material, so a lot of times I'm going to do what's called a Mr. Long definition, my way of wrapping my brain around it, of breaking it down to a more simple language. Some people who teach science don't like that, and if you're taking a science course, an A&P course with another instructor, or a chemistry course, or anything where you're learning this information in this lecture, please be advised that you have to learn it the way that your instructor wants you to learn it. Now, I'm going to simplify it now, and then later on we're going to get into the more technical stuff as the semester goes on. So, if you don't like the way I cover it, oh well. I'm doing it in a way that will help my students understand it. And if you're in someone else's class, you need to learn it the way that your instructor wants you to learn it. Either way, I hope that you find these videos helpful, that you learn something from them, and if you do, please hit like and subscribe, okay? Now, also, I'm a low-tech guy. I got a cell phone, I got me, and I got some markers and a board. This is how I teach normally in a face-to-face session, and since we've migrated to online during this pandemic, I'm trying to deliver the information the best way I know how to my students. So, again, I hope you enjoy this stuff. Hit like and subscribe. Today's lecture is over chemistry. Chemistry is that branch of science which studies the substances that make up what we call matter. Matter is anything that has mass or occupies space. And that includes air. If you blow it up into a balloon, you can see that it occupies the space in the balloon. And the balloon can become heavier or more dense than the air supporting it, and it can fall to the ground. So, it has mass, it occupies space. That's everything in the universe that we can think of that is made up of matter for the most part, okay? Now, when we talk about matter, what we have to, oh, by the way, chemistry is also not just the identification of those substances, but it's the study of how they interact and how they change as they interact to make up the universe around us. I have a strong background in chemistry and a lot of graduate coursework in chemistry and masters in protein biochem. And I understand that if we took 20 semesters of chemistry, we would still be learning. We're just beginning to scratch the surface. And I got 2 lectures to teach you all the chemistry that you need to know for at least anatomy and physiology. So I'm going to pare it down to those concepts and those topics that are important for my students now. If you're in my class, don't read the entire chemistry chapter. There's way more information in it than we can cover in this period of time for you to truly understand anything. So learn the concepts that I cover and that are in my notes set. And if you're in my class, we're in my notes set on page 10. We're going to be following along there. Now, when we talk about matter, we have to talk about the elements. If you've ever seen the periodic table of the elements, the little chart that you get in a chemistry class with all the letters and numbers on it, that periodic table is organized in a fashion that means a great deal of information to a chemist or a biologist and someone who understands it. Many of my students don't have a lot of chemistry background or even a lot of biology background. Or it may have been a long time since they've had it, so I'm not going to go into all the detail of that. That's what your chemistry class is for. But what I want you to understand is this. When we talk about an element is all of the atoms in the universe that exhibit the same behavior. For example, if I have a whole group of atoms whizzing around in the universe, but under specific tests and specific conditions, they always do the same thing as each other, this whole group of atoms, then all of those atoms that exhibit the exact same behavior are considered to be an element. So an element is all the atoms that exhibit a unique behavior. If I have a different group of atoms and they all behave the same as each other, but different than the previous group, then I have a different element. And I'm not really super interested in all of that. I want you to understand this so that it will make sense when we talk about some things in the A&P. When we look at an atom, when we talk about atoms, and if you know if you in my class, you've watched the previous video when we went over the 7 levels of organization that I think are important. The chemical or molecular level. Chemicals and molecules are made up of atoms. And then we went over the organelle, cell, the tissue, organ system, and organism. You need to know those 7 levels of organization. You need to know the definition of them. But in order to understand what chemicals and molecules were, we talked about their collections of atoms. One of the things that we need to know about atoms is this. They are some combination of subatomic particles. The other thing I want you to know about atoms is all atoms are electrically neutral. That means they don't have a positive or a negative electrical charge. Well, what are the 3 subatomic particles? There's 3 subatomic particles that make up all the atoms. One of those subatomic particles is called a proton. And the chemical symbol for a proton is a P with a little plus up where you would have an exponent, okay, or a superscript. So anytime you see this, it means it's a proton. And protons got given that symbol because they exhibit a specific behavior, and all protons behave like other protons. There's another subatomic particle called a neutron. A neutron is abbreviated as an N with a little ought up there where there would be an exponent or a superscript. Neutrons don't have an electrical charge. And then there's one called an electron. And electrons are abbreviated as an E with a little negative charge. And the reason they got these little symbols is because protons behave differently than neutrons, and they both behave differently than electrons and vice versa. And this symbol was just sort of an arbitrary number given to them, saying that they have different behaviors. But for some reason, protons and electrons can attract each other, almost like the positive and negative charges of a magnet. There's a lot of subatomic forces or nuclear forces and things and atomic forces that are holding the atoms together in some ways that are very, very difficult concepts, and we're not even going to go there. But if I wanted to build an atom, I need to have some number of protons and at least some electrons. Hydrogen doesn't have any neutrons. Now, the rest of the atoms are some combination of protons, neutrons, and electrons. When you look at the periodic table of the element, the reason the atoms are in columns and rows the way they are is because certain atoms have certain common characteristics. And we're not going to even get into that level of chemistry. But one of the things that's on that periodic table that you need to know is what we call the atomic number. The atomic number always tells you the number of protons that are in the nucleus of an atom. And atoms have a specific structure with a nucleus and a bunch of clouds of electrons floating around them. And so one of the things you need to know is this. The atomic number is equal to the number of protons in an atom. That's all that it means. But because atoms are electrically neutral, if I know the number of protons that have a positive charge, then I have to have the same number of electrons. So it really also tells you how many electrons there are in the actual atom. The number of neutrons can vary from even within the same atom. One isotope, when we talk about an isotope, iso means same and tope means topography or layout. When we talk about isotopes of the one atom, we can have carbon, for example, can have 12 neutrons or 14 neutrons. We call it carbon 12 or carbon 14. Okay. Actually, it's the atomic mass. But anyway, so some atoms of the same element can have different numbers of neutrons. That's why we're not looking at all that. I don't want to get into that right now. What I do want you to know is this. The atomic number tells you the number of protons. Because atoms are electrically neutral, they have the same number of electrons. And we can look at atoms by knowing their atomic number and doing what we call an electron diagram of the atom. And then that's going to help us predict some of their behaviors. So let me go and erase all of this, and we're going to talk a little bit about more about atoms. Now, when it comes to atoms, one of the things we can draw is what is called an electron diagram of an atom. And scientists have figured out the structure of atoms. There's an area of the atom called the nucleus, And that's where all the protons and neutrons are found, and they're held in there by these nuclear forces. And again, it's a very complex topic, but surrounding that nucleus, electrons are whizzing around in these little areas, and certain numbers of electrons are confined to a certain area that they call an electron cloud or an orbital. And it doesn't mean like, some people describe atoms as kind of looking like our solar system, where the sun would be the nucleus, and the atoms would be whizzing around it like the planets are whizzing around in certain orbitals. It's not quite like that, because they're not just orbiting in a circle or an oval. They can be anywhere within this round sphere of space that we call an electron cloud. Again, that's not super important to us, but we do need to know that the structure of an atom. So when it comes to an atom, if I give you an atom, I'm going to pick sodium. Now, sodium has the chemical symbol Na, and actually it's capital N, little a. That's the chemical symbol for sodium. And it comes from the fact that sodium was originally called natrium in Latin, and that's where the Na for sodium comes from. Now, if I look at the atomic number for sodium, the atomic number is 11. So if I know that sodium has the atomic number 11, it's going to have 11 protons. I'm not going to put the neutrons, but the neutrons would be in the nucleus, and they're all kind of very tightly packed, rubbing around each other and whizzing around inside this nucleus in a very small space. If I know there's 11 protons in there, then there has to be 11 electrons for it to be an atom, because again, atoms are electrically neutral. Now, when we're going to draw the electron diagram, what scientists have realized is that these subatomic particles really are what we call little condensations of energy. That's not the exact way to describe it. And how do we describe energy? I mean, we have an equation, E equals mc squared, Albert Einstein, thank you very much. But what does it really mean? So the way that I try to understand it and get my students to understand it is the way that it dawned on me. The universe is a field of energy. And in some areas of the universe, those little bits of energy are moving around far away from each other. In some areas of the universe, the energy gets packed very densely, and some little bundles of energy, so to speak, start to interact with each other. And then another one might whiz by and interact with this. And as they start to come together, these little condensations of energy, or little bundles of energy, start to form what we call quarks, things that are smaller than the subatomic particles. And then those things start to interact with each other based on their behaviors and their electrical forces and nuclear forces and physical forces. And then they start to form protons, neutrons, and electrons. Protons, neutrons, and electrons come together and form atoms. And we can't really understand these condensations of energy, but we can understand humidity. In South Texas, where I'm at, there's water in the air. Those water molecules are so far apart that we really can't see and touch and feel them most of the time, but they're there. We call it humidity. So between all the oxygen and nitrogen and carbon dioxide and all the other gases in the atmosphere, there's some water vapor out there. Because of the shape of water molecules, and if you do enough chemistry, you'll learn this, because of their physical structure, water molecules have a polarity, and the little positive parts will start to interact with the little negative parts, and if two water molecules come together, they start to hang out together and form some hydrogen bonds. And then if another water molecule zooms by close enough, it might get pulled in by these same forces, and now it continues to grow into a larger and larger molecule of water. And if it gets enough of these small, bundles of water molecules together, they become so dense that the other air molecules can't support them, and they precipitate out of the atmosphere as a raindrop, or as the dew on your windshield when you come out in the morning and you see water or moisture on the blades of grass, and you can feel that. Well, the universe is kind of like that with energy. And these little bundles of energy are whizzing around. If some of them come too close together, they can interact and become larger and larger and larger, forming subatomic particles, forming atoms, forming molecules and chemicals, and so on and so forth. Well, because they're little bundles of energy, sometimes if you put too much energy together, it becomes uncontrollable. And some substances with the same electrical charge can repel each other. Sort of opposites attract. and like charges repel, almost like the ends of a magnet. The positive end of a magnet and the negative end of a magnet will come together, but if I put the two positive ends of a magnet together, they push each other apart. Knowing all of that, they came up with what's called the 288 rule for at least the first 18 or so atoms. And when we talk about what we call the 288 rule, what that basically means is the number of electrons, let me just do it this way. It's the number of electrons that can occupy an orbital. The first orbital can only hold 2 electrons, the second orbital can hold up to 8, and the third orbital can hold up to 8. And it's because of these forces and energies and everything that this rule exists. Now, if I'm going to build an atom of sodium and I know it has 11 protons, then I have to come up with 11 electrons. And since the first orbital or electron cloud can only hold 2 electrons, here, let me change the color of that so we can pay attention to the orbitals separate from the nucleus. So, if I have 2 electrons here, they can be found somewhere in this realm outside the nucleus, but in this space, so we call that the orbital for those electrons. Now, I still need 9 more electrons, so the second orbital can hold up to 8. And I start drawing them in these little electron pairs for these orbitals, and there's some reasons in chemistry and physics for all of this, but we're not going to go into it. I still need 1 more electron, and it'd be nice to just cram it into this orbital. But this orbital is completely filled with all the energy and the electrons that it can hold, so we have to kick that electron out into one orbital by itself. And this would be the electron diagram for the atom sodium. I got 11 protons. I have 11 electrons distributed in 3 orbitals according to the 288 rule. And the outermost orbital, by the way, is called the valence orbital. And you need to know that. The valence orbital is the outermost orbital. Now, I don't like to give human attributes to non-human things, but suffice it to say this. The outermost orbital isn't quite satisfied. It's not completely balanced electrically unless every slot for some energy for an electron is completely filled. And this valence orbital is not. What I need to do to fill it is get 7 more electrons and cram them in here. Or what if I could just say, you know what, let me kick this electron off into the universe, and this becomes the valence orbital. And that's exactly what sodium can do. So I'm going to erase some of this information here now. And what happens with the sodium atom is it is electrically neutral, but its valence orbital is not quite balanced out properly. So a lot of times it'll kick that electron off into the universe and release it. And when it does so, now I have a sodium atom that has 11 protons, but only 10 electrons. If I do the math, I have 1 extra positive charge. I have 1 more proton than neutron. So if I write this chemical symbol down, a chemist looks at that and says, that's the sodium, that's the symbol for sodium. It has 11 protons and 11 electrons. It's electrically balanced. But if I were to do this, they know that's no longer a sodium atom. That's called a sodium ion. The definition of an ion is just an atom that has gained an electrical charge. It's an electrically charged atom. And the way that atoms, at least in the simple ones, gain electrical charges is by losing electrons or gaining electrons. And since I've lost one of my negative charges, the sodium ion has a single positive charge. And it falls under a category that we call a cation. So if you see this term, the T in cation looks like the positive sign. So cations are always positively charged ions. Okay? Now, we can look at the electron diagram. The reason this becomes important is because once we know the atomic number and we can draw the electron diagram, we can very often, not always, but often predict which atoms will ionize and which one will not. And once they gain that charge, they tend to want to interact with other things that have the opposite charge, just like two magnets want to come together. And we can form bonds between ions called ionic bonds. So a couple of things you need to know. You need to know the definition of matter. You need to know that an element is all the atoms that exhibit specific behavior. You need to know that all atoms are electrically neutral and made up of 3 or 2 out of 3 of the subatomic particles. All atoms have all 3 except for hydrogen. We'll talk about that later. Hydrogen doesn't have any neutrons. The atomic number of an atom tells you the number of protons in the nucleus, and since they are electrically balanced, then we therefore know the number of electrons surrounding the nucleus in the orbitals. And because we know the 288 rule, we know that the first orbital can hold 2, the second orbital can hold 8, the third orbital can hold up to 8. Beyond that, the chemistry gets fuzzy and the physics gets really fuzzy, and we're not going to go there for now. So, let me draw one more, and I want to show you. I just want to illustrate something to you. I'm going to erase this sodium atom, and I want to do one more atom for you. I might do a couple more, but then we need to wrap up this video before it gets too long and too boring, all right? So now, I'm going to do an atom of chlorine. The chemical symbol, Cl, that's for chlorine. And we know that the atomic number is 17. So if I were going to draw the chlorine atom, I could do this. It's got 17 protons. It's going to have 17 electrons if I draw the atom. Now watch. Due to the 288 rule, I can have 2 electrons in the first orbital. I can have up to 8 in the second orbital. And I can have up to 8 in the next orbital. But in the next orbital, I only have 7 because the atomic number is 17. 1, 2, 3, 4, 5, 6, 7. That's what the atom, the electron diagram of the atom chlorine looks like. Now again, if we look at the valence orbital, are all the slots completely filled with electrons? And the answer is no. I need one more electron to fill all the little slots that are available to it, so to speak. So I can either get rid of 7 electrons and make this one the valence orbital, or I can gain 1 electron. And if Mother Nature is nothing else, she is efficient with the movement of energy. So if I had 1 A&P textbook on a table over here, and I had 7 A&P textbooks on a table over here, you know how heavy those books are. If I told you I need 8 of them together, it would be easier to move 1 book to this table than to move all 7 over here. So Mother Nature will always conserve energy in moving things around, so to speak. So what happens is, let's say there's an electron that got kicked off from another atom somewhere, maybe from sodium or potassium or one of these cations. If this electron whizzes by too close, it can get pulled in here and join the chlorine atom. And now the chlorine atom, which has the chemical symbol this, becomes this. Because it has 17 protons, but now it has 18 electrons, and when you do the math, it has 1 extra negative charge. So this is the ionic symbol for the chloride ion. The chlorine atom, the chloride ion. And it is called an anion because anti means against or not, and it has a negative charge. All cations are positively charged ions. All anions are negatively charged ions. And we can see how one atom can kick off an electron that it doesn't need and ionize, like sodium ionized, to get a positive charge and release an electron into the universe. And we can see how other atoms need an extra electron and they will take it in and they will gain a negative charge. On some occasions, an atom can kick off 2 electrons, like calcium and magnesium and iron, and get 2 positive charges. And in some instances, we have atoms that can take on 2 electrons and get 2 negative charges, although it's kind of rare, but there's some chemistry that's pretty cool there. So now you guys understand, I hope, at least what the electron diagram tells us. It allows us to predict if an atom will ionize or not. And not all atoms ionize very easily under normal conditions. but some of them do. So when you look at the periodic table of the elements, all of the ones in that first vertical column tend to ionize pretty easily, and they tend to give off their electron. For example, I'm going to do one more diagram of an atom for you. Okay? I hope this is making sense, and I hope you're understanding it. If not, you might need to watch other videos from another instructor who teaches better than me. I don't know. But if we did hydrogen, H is the chemical symbol for hydrogen. The atomic number for hydrogen is 1. So hydrogen has 1 proton, and it has 1 electron whizzing around its nucleus. There's no neutrons. When hydrogen ionizes, it will kick this electron off into the universe and simply get this symbol, which is really nothing more than a proton by itself. So hydrogen ion is a proton without its electron. Why and how all of this happens is some real complex physics and chemistry, and I'm not going to get into all the atomic forces and everything, but nonetheless, be able to draw an electron diagram. If I give you an atom and I give you the atomic number, you should be able to draw the electron diagram, and you should predict if it will ionize or not. And you should predict if it will become a cation or an anion. Will it lose electrons and gain a positive charge? Will it gain electrons and get a negative charge? Again, not all atoms ionize. I'm going to draw one more for you. Let's draw helium. Helium has the atomic number 2, so it has 2 protons. It's going to have 2 electrons in its valence orbital. Is its valence orbital completely balanced and filled? And the answer to that is yes. So is there any need to gain or lose electrons? And the answer is no. So helium doesn't ionize very easily. That's why in some textbooks you'll hear about, if you do enough chemistry, you'll hear about the inert gases. It means it's not moving, it's not going to change. They don't do a whole lot. They don't ionize. Another one would be neon. Neon has the atomic number 10, so it's got 10 protons. It's going to have 10 electrons, the first orbital, the second orbital. And look, due to the 288 rule, its outermost orbital or valence orbital is filled. So neon does not ionize very easily. So we can look at the valence orbital, count the number of electrons, and determine whether it's going to gain or lose an electron or two in order to ionize. If it gains electrons, it becomes more negative, becomes an anion. If it loses electrons, it becomes more positive, becomes a cation. All right? Now in a minute, I'm going to explain to you why all of this stuff is important. One of the reasons it becomes important is because some of these ions can form chemical bonds with each other. And the strength of these bonds and the way that the bonds are formed are different. So we can talk about hydrogen bonds, you can look that up. We can talk about ionic bonds, and we can talk about covalent bonds, which are 3 of the most common types of bonding between atoms and molecules and substances. So, I want to talk to you about this, though. The reason ions are important is because 2 oppositely charged ions can form a chemical bond, and we call it an ionic bond. Now what happens is this. Let's say I have sodium, which is ionized, and it's kicked an electron off into the universe. And then chloride picks up that electron and becomes negatively charged. If these 2 ions come close to each other, they can form a substance called sodium chloride, a positively charged sodium ion and a negatively charged chloride ion. If we were to draw the atomic number or draw the electron diagram for potassium, when we look at potassium, we realize that potassium will do the same thing that sodium does. It has 1 electron in its valence orbital, so it will kick that electron off and become balanced in its valence orbital. Well, if I take a potassium ion plus a chloride ion, I can form potassium chloride, and they form a bond because of their negative charge. Again, it's electromagnetic attraction, like 2 magnets. Or if I have calcium, if you look at the atomic number for calcium, calcium will lose 2 electrons and gain 2 positive charges, and it will have 2 more protons when it ionizes. If I combine calcium with chloride, I would get this, but they're not equal in the number of charges. Oops. Should have done that. So I need one more chloride to balance out those two positive charges. And then when calcium chloride is formed, I get CaCl2 because I have two positive charges and now I have two negative charges. And then we can get into chemical formulae and balancing equations. But what I want you to see is that anytime I have a positively charged ion and a negatively charged ion, they can form chemical bonds. One last example would be this. If I have a sodium ion and I have what's called the iodide ion, iodine can gain an electron. They can come together to form sodium iodide, or I can form potassium iodide. A positive cation, a negative anion, can always come together to form an ionic bond. So, we're going to see why ions are really, really, really important in anatomy and physiology later on. But I wanted you to understand the atomic structure, the electron diagram, that the atomic number tells you how many protons there are, therefore how many electrons there are, how we draw it out, and that way you should be able to predict if some of these substances, some of these atoms will ionize or not. Some of them don't ionize. So I'm going to do one last concept and then I'm going to wrap up this video and we'll finish up some chemistry in another video. Okay? I'm going to give you one more example. If I look up carbon, carbon has the atomic number 6, so I know it has 6 protons in the nucleus. So it's going to have 6 electrons. There's 2 in the first orbital, and I have 4 of them floating around out here in the valence orbital for 6. Is it easier to gain 4 or lose 4? Well, it's about the same. And it turns out that carbon doesn't gain or lose electrons at all. What happens is it can share this electron with another substance that might need an electron. For example, if I have a hydrogen atom here that has a proton, it has a single electron out here whizzing around. What if these two guys kind of hung out together, so for a little while the 2 electrons were around here and this one's electrically balanced, but then this electron also goes over here and gives this one its partner. And if I did that 4 times, if this carbon atom will share these electrons with these 4 hydrogens, then because they're sharing valence electrons, they are called covalent bonds. In an ionic bond, one atom will ionize and give an electron to another. In covalent bonds, some of the time these 2 electrons will be whizzing around the carbon atom, other times they'll be whizzing around here. And if carbon does that with 4 different hydrogens, then it can have 8 electrons here sometimes and share those electrons with these 4 hydrogens. And we draw that substance as CH4. We know that in organic chemistry as methane gas. So, because they're sharing valence electrons, we call those covalent bonds. I wish I had more time to tell you how and why we could predict that, but just know that carbon will form covalent bonds with other substances. But some of these substances we can predict will ionize, especially if there's only 1 or 2 electrons out here, or they only need 1 or 2 electrons to fill the valence orbital. Everything else gets a little tricky, and this is not a chemistry class, so I don't want to spend too much time. I've already spent more time than I like doing this. So, I hope you enjoyed this. I hope you learned something from it. I hope you learned that the definition of matter, the definition of an element. I hope you learned the 288 rule. The atomic number tells you how many protons and therefore how many electrons there are. And you know how to draw an electron diagram. So if I gave you an atom with an atomic number, you should be able to draw an electron diagram and figure out if it will or will not ionize, and if it becomes a cation with a positive charge, or if it will become an anion with a negative charge. That's all that I want you to know so far for this class. And then know, because of those electrical charges, they like to interact with other substances. We'll look at the importance of ions again later on. Again, I hope you learned something. I hope you had as much fun as I did. Go do this stuff till you can't stand it, and then do it some more until you understand it. Okay? See you in the next video.